In 1969, a book convinced most of the field that neural networks were a dead end. The authors weren't outsiders. Marvin Minsky and Seymour Papert were among the most respected researchers alive, and their critique was rigorous enough to end serious funding almost overnight. For 17 years, almost no one touched the idea. Then, in 1986, two researchers published a result the field had assumed was impossible. Their names were Geoffrey Hinton and David Rumelhart. What they showed didn't just revive an abandoned idea, it exposed something the 1969 argument had missed. By the end of this video, you'll understand what neural networks actually are, why serious researchers abandoned them twice, and what that 1986 result actually claimed.
Plain machine, AI in plain English. We're tracing the complete history, from the very first idea all the way to the present. Let's continue.
To understand neural networks, don't start with computers. Start with something simpler: how a person learns to sort mail. Imagine training someone to sort letters by likely destination without giving them a rule book. Instead, you show them a letter, they guess, and you tell them whether they were right. Wrong guess, they adjust whatever internal instinct led them there. Right guess, they reinforce it. After thousands of letters, they get good, not because you told them the rules, but because their internal sense of what a match looks like was slowly reshaped by feedback. That is roughly what a neural network is. A system built from many small decision units, called nodes, organized in layers, connected to each other by adjustable strengths, called weights. A piece of data goes in one side, a prediction comes out the other. If the prediction is wrong, the weights shift slightly, nudging the network's next guess a little closer. No one writes the rules for what a weight should be. The network arrives at them by being shown examples and adjusting after each one. The same basic principle as the mail sorter, just formalized into numbers and layers. The idea itself is old. In 1943, Warren McCulloch and Walter Pitts proposed a simple mathematical model of a neurome, an on-off unit that could, in principle, be wired together to compute anything a conventional computer could. In 1958, Frank Rosenblatt built on that idea with something called the Perceptron, a physical machine that could learn to recognize simple patterns by adjusting its own connections. Newspapers at the time predicted it would eventually walk, talk, and think. Act 1 optimism playing out again in a different discipline. This is the fundamental architectural difference from expert systems, which you saw in video 8. An expert system's knowledge lives in rules someone wrote down. A neural network's knowledge lives in the pattern of its weights, a pattern no one could have written. It emerged from exposure to data. That's the concept. The mechanism by which those weights actually get adjusted, the specific algorithm that made this practical at scale, is a story with its own name, its own history, and its own video. For now, what matters is the architecture, layered, weighted, and shaped by data rather than instruction. This is called a neural network. The approach behind it is called connectionism, because intelligence in this view isn't a set of rules, it's a pattern of connections. In 1969, Minsky and Papert published a book simply called Perceptrons. It was a work of real mathematical rigor, and its central result was narrow but devastating. The simplest kind of neural network, a single layer with no hidden layers between input and output, could not solve certain basic classification problems. The example they used was elegant. A single-layer perceptron cannot learn the exclusive OR function, a simple logical pattern a child can grasp intuitively. If the simplest form of the architecture couldn't handle something that basic, the argument went, the architecture itself was fundamentally limited. What Minsky and Papert did not claim, but what the field concluded anyway, was that adding more layers wouldn't help. They suspected it might, but training a multi-layer network was, at the time, an unsolved problem. No one knew how to make it work in practice. So the distinction between a narrow mathematical result about one specific architecture and connectionism doesn't work collapsed. Funding agencies, already cautious after the first AI winter, read the book as a verdict. Grant money for neural network research all but disappeared for most of the 1970s. This is worth sitting with, because the pattern should look familiar from earlier in this series. A real, specific, technical limitation was generalized into a verdict on an entire research direction. The same move that hardened the field's overconfidence before the first winter. The difference this time was that the verdict was mathematically grounded. That gave it more staying power than the earlier overpromising ever had. Not everyone left. Through the 1970s and into the early 1980s, a small number of researchers kept working on multi-layer networks anyway, mostly outside the mainstream AI funding structure, often in psychology and cognitive science departments rather than computer science ones. Among them were David Rumelhart, a cognitive psychologist, and Geoffrey Hinton, who trained originally in experimental psychology before moving into what was, at the time, a genuinely unfashionable corner of computing. They were part of a loose research community that came to be known as the PDP group, Parallel Distributed Processing, built around a simple, almost stubborn premise that the brain doesn't compute with explicit rules, and maybe machines that learn shouldn't either. This was not glamorous work. There was no expert systems-style commercial market for it, no consulting contracts, no $600 million industry. What there was, instead, was a specific, unsolved technical question. If multi-layer networks could, in principle, get around the limitation Minsky and Papert identified, how would you actually train one? How do you adjust the weights of a hidden layer, a layer with no direct connection to the right answer, when all you know is whether the final output was correct? That question sat unanswered for most of 2 decades. Solving it required a way to send the error backward through the network, layer by layer, so that every weight in the system could be nudged in the right direction. Whoever solved it wouldn't just be fixing an obscure technical detail. They would be answering the specific mathematical objection that had frozen an entire field's funding for a generation. In 1986, Rumelhart, Hinton, and a colleague named Ronald Williams published a paper demonstrating that multi-layer networks could, in fact, be trained reliably and at meaningful scale. The specific mechanism behind that result is its own story, one detailed enough to deserve its own video. What matters here is what the result meant. It did not just solve a training problem, it answered the Minsky-Papert objection directly. The limitation of 1969 applied to networks without hidden layers. Networks with hidden layers, trained properly, did not share that limitation. The ceiling that had justified 17 years of funding decisions turned out to be a property of the simplest possible version of the idea, not the idea itself. The paper did not make headlines outside the field. It did not rescue any commercial product. What it did was quieter and, in retrospect, more important. It gave connectionism a technical foundation solid enough to be taken seriously again. So, what does this history change about how you should evaluate an AI system today? The expert systems era taught you to ask whether a domain is closed enough for handwritten rules to hold up. Neural networks flip the diagnostic question. A learned system doesn't have a rule book you can inspect. Its knowledge lives in millions of adjusted weights shaped by whatever data it was trained on. That creates a different kind of risk, not a smaller one. Two scenarios are worth working through. Scenario 1. A vendor tells you their system learned this from the data rather than following hand-coded rules. That framing sounds like an advantage. No brittle rulebook, no maintenance ceiling. But the diagnostic question changes. It's no longer what happens at the edges of the rules, it's what was in the training data and what wasn't. A learned system inherits every gap, every skew, and every blind spot in whatever it was shown. And unlike a rule-based system, you often can't simply read the weights to find out where those gaps are. Scenario 2. You're comparing two systems for the same task, one rule-based, one learned, and trying to decide which is more trustworthy for a high-stakes decision. The honest answer is that neither architecture is inherently safer. A rule-based system fails predictably at its stated boundaries. A learned system can fail unpredictably inside its boundaries in ways that only surface when the data it encounters diverges from the data it was trained on. The lesson from 1969 and 1986 isn't rules bad, learning good. It's that every architecture has a ceiling, and the honest question is always the same one. What is this system's ceiling, and how would you know if you hit it? That question will keep recurring through the rest of this series in different forms as the architecture keeps changing. The details change, the question doesn't. Here's the shape of what happened. In 1969, a real and narrow mathematical result was generalized into a verdict on an entire approach to intelligence. That verdict shaped funding, careers, and the field's collective attention for almost 2 decades, and it was wrong. Not because the mathematics was flawed, but because it was mistaken for a bigger claim than it actually made. Neural networks weren't the new idea in 1986. They were an old idea, declared mathematically dead in 1969, that a handful of researchers refused to let stay dead. What changed wasn't the ambition, it was the proof. Act 2 of this series was about architectures that hit ceilings they couldn't see past. Act 3 is about an architecture built specifically to keep learning past wherever its current ceiling happens to be. That's not a small shift. It's the shift that makes everything from here forward possible. In the next video, we go back to that unanswered question from earlier. How do you actually train a network with hidden layers? How do you take an error at the output and figure out which of thousands of internal weights caused it and by how much? The answer has a name: backpropagation. It's not just an implementation detail. It's the specific piece of math that turned neural networks from a promising idea into something you could actually build. Once you understand it, you'll understand why almost every AI system built in the decades since, including the ones in the headlines today, is, underneath, still running on the same basic principle Hinton, Rumelhart, and Williams worked out in 1986. That's video number 10. Subscribe if you want the full arc. Each video in this series builds on the last. The AI glossary is in the description. 30 terms, plain English, free. This is Plain Machine. Thanks for watching.